said that this is the definition of conditional probability, right? Probability of A given B. And we said that we showed why this would be a good formula for it. Probability of A intersect B given the probability of B. So we use that. Then we said, we had some problems. We said box 1 is green, has 4 blue and 8 yellow, box 2, 2 blue and 10 yellow. And we asked questions. Suppose we select a box at random and then select a ball at random. We can ask questions like, what's the probability of getting a blue ball given that we selected box 1? So that would be written like this, right? Given box 1, the probability of a blue ball. Okay, a more confusing question was, what is the probability that we selected box 1 given that the ball is blue? So how would we write this question? We would say, given that the ball is blue, what's the probability that it's box 1? And then we said that, so we had that. So we had this, sorry. And then Bayes' theorem will allow us to reverse the order if we want. So this was one form of Bayes' theorem, and I think I proved that here. And we looked at this kind of picture, and we saw that B can be written as this union this, where A bar stands for the complement of A. So B can be written as the union of this. And we also said that this union, each piece has nothing in common with the other one. So they're disjoint. We call them disjoint, or mutually exclusive. So when they are disjoint, you can change the probability of a union into the probability of the first one plus the probability of the second one. So that turns out to be useful. And now we want to see how Bayes' theorem is derived. So we start out with this. It's just the definition. Then we move this over to here. And so we have this so far. Then we have, that's what I have here. And then this is just the definition again. But now instead of A intersect B, I'm going to write A intersect B as B intersect A, which is this. So instead of A intersect B, I have this. So I just put that there. Then I have A intersect B on the bottom and this on the bottom. Then this one is A intersect B. That was the same as this one. So I already replaced this one with this one here. So I can do the same thing, put the same thing down here as well, right? And then the other piece, you get the same thing. We do the same thing, but with A bar instead of A. And so we have Bayes' theorem. And the point here is that here we had A given B, but here we have B given A. Okay, only B given A's, or B given A bars, but we don't have the reverse. So, of course you don't have to do this. If A given B is easier to calculate than B given A, then there's no reason to bother to do this, but this allows us the option of doing it this way. Okay? And then here I talk about what if you have the whole space is divided into more than 2 pieces. You can still write Bayes' theorem, and you get this form here. This is from Wikipedia, versus this form, which is the form we just derived. Okay, so just a little bit more here. Okay? And then we mentioned this terminology. The posterior probability of y given x, that's this one here, is the posterior probability of y given x, or the conditional probability of y given x. And it can be estimated by the prior probability of y, but only estimated because there's other factors involved. Okay, and now we talk about the naive rule, and this is the benchmark to measure all other classifiers. What was the naive rule? Not the naive Bayes rule, but just the naive rule. So we have some data, we have a bunch of predictors, which we call x1 is one predictor, x2 is another predictor, x3 is another predictor. We might have, so like in the golf example, how many predictors did we have? Do you remember what they were? Like golf playing, what were they? Can you remember? What was one of them? Overcast or not? Yeah. Okay. Sunny and so on. Yeah, that was one. What was another one? Humidity, and that could take on how many values? Humidity was only high and normal. Okay, and then what else? Well, that was what we're trying to predict. That's not the predictor, that's the class. Okay, see, we don't remember, right? But what? Temperature was another one, and windy was another one. So I think there were 4, plus the class variable, which was play, not play, right? So we would have 1, 2, 3, 4 predictors in this case, okay? So x1 would be windy or not windy, x2 would be high pressure, low pressure, x3 would be temperature, right? Okay, so these stand for the predictors. Okay, so what is the naive rule? If we're trying to predict whether people are going to play or not, how do we do it if we use the naive rule? The naive rule means we ignore all the predictors. Ignore them completely. Ignore all that data, which is obviously a waste, but that's what we could do. We would ignore all the, and how would we make the prediction? Well, in that data set there were 4, let me show you the data set, by the way. I think I have it here. Maybe not. Here, this was the data set. In this data set there were 14 rows of data. So what do you do for the naive rule? You just see, were there more, which was the highest, what was the majority class here? Well, there are only 2 values for the class, right? No and yes. So which one occurred more? Yes. So therefore, what's the naive rule? Anytime you ask the question, will this group play golf or not? You're going to say yes. You ignore all the other data, all the other predictors, I'm sorry, right? That's called the naive rule, okay? So, that's the naive rule. So how do we put it? Super simple rule for classifying a record into one of m classes. How many classes are there in this problem? M equals the number of classes is play, not play. So there's 2. So m equals 2 in this problem, okay? If we were trying to predict people's beer preference, and suppose we had Asahi, Sapporo, Kirin, then what? M would be what? 3. Okay, 3 different values for the class. Okay, M is just that. Okay? In this terminology. Okay? So, super simple rule for classifying a record into one of m classes, ignoring the predictor information, classify the new record to the majority class. Okay? Hopefully other classifiers will do better than this, since they will include information given by the predictors. Okay, here I'm using the word predictors, and other times I use the word inputs, right? You know, you can use a million different words. Okay? First we will introduce what is, okay, now we're going to talk about naive Bayes. So we already talked about what the naive rule is. That's very simple. Now we're talking about naive Bayes. But before that, we're going to introduce what's called the complete Bayes. Naive Bayes makes a simplifying assumption on complete Bayes, which makes the calculation easier. Okay, complete Bayes is very intuitive. The whole subject of data mining can be summarized by saying that we are trying to decide what class a particular instance should be assigned to, right? You get a new class, you want to predict what it's going to be. For example, X is a new customer. Which of our products should we try to sell him or her? So we try and classify this customer, this new customer, as they're going to be most interested in this product, right, versus that product, right? So we have, in that case, each product that we have would be a class, right? Maybe we have TVs, computers, toys, and TVs, computers, games, and washing machines, okay? So here comes a new customer into our store. Which one are they going to be interested in, right? We're going to classify them before they come in. We want to send the right person to them. So before they ask a question, we want to classify them and say, what are they going to be interested in? So how many classes are there in that case? How many classes in that example? So I said TVs, computers, games, and washing machines. So how many classes are there? 4. Okay? So here the instance is X, and the classes are listed, are the list of our different products, right? X being like the new person. We are classifying X as liking here dark chocolate versus milk chocolate. Okay? So, all right? So complete Bayes answers the question, which class should I assign to instance X? And the answer is given in the very intuitively simple way as follows. So what's the complete Bayes? This is not the naive Bayes rule. This is the complete Bayes rule. So what is it? What's step 1? You can read it right here. What is step 1? Find all the other records just like X, i.e. where the predictor values are the same as with X. So let's talk about this example I'm talking about, where a person walks into our store, and we have these 4 classes. We're trying to classify them into 4. Now suppose we have already some data on each customer that walks in. For example, we know their income. Suppose we know their income, and we know their gender, and we know their age, and we know, what else could we know about them? Okay, we know whether they're married or not. Okay, good, that's good. So that's the 4 variables, 4 input variables, or 5, whatever it was. Okay, so let's write those down. So what did we say? We know their age, we know their gender, we know their income. What else did we say? Marriage status, marriage or not. What else? Anything else? Just those. Let's say we just know those. Okay. So now, so we already know about. We have a database of 2,000 customers, and we know with each customer we know age, gender, income, marriage, and what they were interested in, which class. So this person was 34, male, $55,000, not married, and they were interested in game. Okay? And this person was 22, female, 20,000, not married, and they were interested in game. Okay, and so on. So we have, let's say we have 2,000 customers. We have this information for all of them. You understand? Okay, so this is our, we can build a model based on this. How do we build the complete Bayes model? How do we do it? Here's how we do it. What do we do? Step 1 is what? Find all, so a new person comes in. Here's our store. Here's the door. Somebody's coming in. Right? Here they are. Right? And it turns out that they're what? They're 32 years old. They're a woman. Their income is $40,000, and they're married. Okay? New person comes in. Which class should we assign them to? That's our question, right? Right? That's our question. How does the complete Bayes answer this question? Again, what does number 1 say? Find all the other records. What other? From where? Other records where? From the 2000, right? From here. Find all the other records from there that are exactly like our record, our new person, right? So we have to just go through here and find all the other people, all the other women who are 32, make this amount of money, and are married. Now, there may not be anybody in the database like that, right? Or there may be a few people like that, right? But this is the way it works. 2, from all those people that are exactly like this person, what? Determine what classes they all belong to. So some of them are going to belong to the game class, and some of them are going to belong to the washing machine class, and some of them are going to belong to the computer class and the TV class, right? So determine, what are the classes that they all belong to? So suppose there are 6 of them exactly like this person that bought computers, and there are 4 of them exactly like this person that bought washing machines. Okay? And suppose that's the only customers that were exactly like this customer, there were only 10. Okay? And 6 of them were like this, and 4 of them were like that. Okay, understand? In our database, 6 people who were exactly like this person, this new person that just walked in, were interested in computers or bought a computer. And 4 people who were exactly like this person that just walked in, bought a washing machine. So what should we classify this new person as being interested in? This one, right? Being interested in computer, right? Because there's more people that were interested in computers that were like this person than washing machines. So that's the rule. So determine what classes those all belong to, and which class is most prevalent. Assign that class, the most prevalent class, to the new record. Right? Do you understand it? Okay, it's very natural. So we said, so complete base answers the question and is given in the very intuitive and simple way as follows. Okay, is that clear? All right, so that's complete base. Now what's the problem with complete base? Well, this number, suppose we measure this in dollars. Okay, now this is 40, maybe it was 4681. Okay, now how many other people are going to earn exactly that amount of money? Probably nobody, right? So the problem is that we're not going to find people that are similar to our person. Okay, now you say, okay, well let's measure it. We don't need to be so precise. Let's just measure it like 40 to 41, 41 to 42, or maybe even 40 to 45, 45 to 50, and so on, right? Okay, but still, you're still going to have a lot of different possibilities here, and it's very likely that you may not find anybody, or just maybe 1 or 2 people that are exactly like your client. Okay, so you're going to have trouble because of that. So, like, suppose you didn't find anybody in here, then you would have no idea how to classify them. Or suppose you only found 1 person, so you're going to classify them just like that 1 person, but obviously that's pretty weak, right? It's not very strong evidence about what you should do. Okay, so that's the problem with the complete base. So once you start getting a lot of variables, you start getting a lot of possibilities, and once you get so many possibilities, chances of finding that person in your databases gets much smaller and smaller. So you get weaker and weaker evidence. Okay? On what to do, yeah?
What if the number of classes is the same?
What if if they're both the same? What do you want to do? Huh?
Just choose either.
Yeah, right. Nothing you can do then, right? Okay. In addition, it may be useful to change the method so that it answers the question, what is the estimated probability belonging to the different classes, and then which class is most probable. So we might do this. So we get this new person. We might try to predict not only which class should they be in, but what's the probability of each class. So here we might have said that there were 6 people like this and 4 like this, so maybe we would say that the chances are that they should be in this class are 6 out of 10, and the chances that they should be in this class are 4 out of 10. So not only do we have the class that we choose, but we also record the probability for each of the classes. We're still going to choose the class with the highest probability, right? But we also keep a note of those probabilities. Okay? That's going to turn out to be something we'd like to do, is keep a record of the probability. So what's the probability that they are in this class? Suppose we had like also one more class, let's say 3, which was TV. Okay? So we just keep a record of the probabilities that they're in each of the classes. Okay? Understand? So in addition, it may be useful to change the method so that it answers the question, what is the estimated probability of belonging to the different classes? And then, which class is most probable? So after we make a record of the probabilities, then we still answer the question, which class is most probable? Okay? Everyone follow this so far? Okay. So conditional probability again. Let xi represent the different predictors. So here we had, the predictors are 5, 4, 3, 2, right? Those are the predictors, and the class is 1. Let Cj represent the different classes. So, I'm sorry, I did that wrong. These are the predictors, and this is the class, right? I'm sorry, I said that wrong. So how many C's are there? There's a C1, there's a C2, is there a C3? No. What's C1? Might be play, C2 might be no play. Okay, C just stands for the C1, C2, and so on, stand for the possibilities. In this notation, it stands for the different possibilities for the class. Okay, is this clear? Okay, Xi stands for the X1 might be outlook, X2 might be temperature, X3. So there's a little bit, actually, there's a little bit of inconsistency in this notation. Because these different values represent the values that this variable can take, whereas these represent different variables, not the different values that each variable can take. Do you agree with me? A little bit of inconsistency in this notation, right? But anyway, we can't do anything about that. Okay, recall the golf playing example. The Xi are outlook, temperature, humidity, windy, and the Cj are play and not play. We can write something like this. The probability of class value j occurring given certain values of the predictor variables. So this might be, for example, the probability of not play given that it's windy, high humidity, high temperature, or something like that. Okay, understand the notation? Okay, again, there is a little bit of inconsistency in this notation, but anyway, we'll have to live with that. Okay, to classify a record, we compute its probability of belonging to each of the classes Cj. That's what we said. That's what I did here. I said, okay, I think this one is probability. This is 6/10, 4/10, and something else. Okay, so we compute the probability that it belongs to each of the Cj records. Note that the above means that the Bayes classifier worked only with categorical predictors. Okay, so everything we're talking about here are categorical predictors. If we use a set of numerical predictors, then it would be very unlikely that any two instances, that's what I said here, right? When I said their salary was 40681, then it's going to be so unlikely that another one is going to be exactly like this. If we have just categorical predictors, we don't have so many different possibilities, so it's more likely to work. The complete Bayes is more likely to work. Okay? Therefore, numerical predictors should be binned. What does that mean, binned? What do you think that means? Anybody guess what that means? Yeah. For example, what would I do? How would I take the income variable and bin it? Huh?
High income,
Sorry?
like high income and medium income.
Yeah, okay. Like low income, medium income, high income. Or we could say, 10 to 20,000, 20 to 40, 40. That's still binning it, right? Okay? So therefore, numerical predictors should be binned. Okay, let's look at this data. Simplified data set. We're just looking at humid versus not humid, and play versus not play. So suppose we had a data set of 1,000 people, and there were 50 people who did what? In the case where it was humid, they didn't play. And there were 50 people in the case where it was not humid, they didn't play. And there were 180 people in the case where it was humid, that they did play, and there were 720 people in the case that it was not humid, that they played. Okay, understand this database? Okay. We're trying to predict play versus not play based on just one predictor, humid versus not humid. Okay? Or high versus low or something like that. X is, so what's X, what would X stand for in this case, in this notation? X would stand for one of the predictors. In this case, we only have one predictor. So X stands for that, so X is humidity. Okay? And C stands for the class. So we might say that C1 is not play and C2 is play, something like that. Suppose we actually have 1,500 records, but the above is the training set. So here the total is 1,000 records. This is our training set. But we have actually 1,500 records. We're going to use this for our training set. So this is still about the full classifier or the exact classifier, not the naive Bayes classifier. Suppose now that we have a new record to predict as to whether they will play or not, and we want to use our training data to make the prediction. If for the new record it is humid, so if it's humid, then what should we do? So in the case of humid, we had 50 that not play and 180 that did play, so what should we predict? Obviously, what? That they're going to play, right? Given that it's humid, we're going to predict that they play, right? So if for the new record it is humid, the probability of not play is 50 out of 230, right? Out of the total number of humid records, it's 50. There were 50 out of 230, so the probability is 50 out of 230 that they won't play, and the probability of belonging to the other class, the play class, is 180 out of 230, right? Does everyone agree? That clear? So using the assigned to the most probable class rule, we would say what? That they're going to play, right? Because 180 out of 230 is more than 50 out of 230. And if we want to do this as well, we said in addition it may be useful to change the method so that we answer what is the estimated probability of belonging to the different classes. So what's the estimated probability of belonging to the not play class, given that it's humid? 50 out of 230, right? What's the estimated probability of belonging to the play class? 180 out of 230, right? So those two numbers, those two fractions. So note that even if it is not humid, however, okay, so do you see what, so anyway, so if it's humid, what are we gonna do? We're gonna predict what? Play, right? How about if it's not humid? Oops, sorry. How about if it's not humid? What are we gonna predict? Play, right? So actually, whether it's humid or not, we're gonna predict what? That they're gonna play, right? According to this rule. Everyone agree with that so far? Okay. So note that even if it is not humid, we still will assign the class play. So actually in this case, the classification results are the same as using the naive rule. Because what would the naive rule give us here? What's the total number of not plays? 100. What's the total number of plays? 900. So if we just use the naive rule, we ignore whether it's humid or not, we would say what? We assign the most probable class, which is going to be what? Play. So using the complete Bayes actually doesn't do any better than what? For this data set, doesn't do any better than the naive rule. Okay? Any questions so far? Okay, now we have something called the cutoff probability method. Suppose we are more interested in identifying instances of not play. So, and we don't care so much about misidentifying records that are play. So for some reason, we just want to, we don't care if, sometimes when somebody comes in, we say they're not going to play and they actually play. But we don't want to miss the not plays. Okay, you understand? Now, I don't know why we would, well, here, maybe if people not play, we don't mind shutting the golf course to save money or something, shutting down the golf course. So maybe that's what we're concerned with. We've talked about other cases where you are more concerned with one type of error than another. The cancer screening examples we discussed in class, for example, right? So we don't want to classify somebody as not having cancer when they actually have it, and I'm more willing to make the error of classifying somebody as having cancer when they don't have it. I don't care so much about that because that just means I'll have to submit them to one more test, maybe some other test that may be a little bit more invasive or troublesome test, but that's not so terrible versus sending somebody away, telling them they don't have cancer, and then they get sick and get very sick, and then they have much more serious problems. Okay? So again, suppose we're more interested in identifying instances of one class, and we don't care so much about misidentifying records that are of other classes. Okay, just suppose in some cases that will be true, and so in those cases we might think about the following. Our approach will be to establish a cutoff value for the probability of an instance being not play. Okay, and classifying all records above that probability as not play. So let's say for cancer, let's think about it for cancer. So what should we do? We want to have a cutoff value. So that if the probability that someone has cancer, normally it would just be 50-50, right? If it's above 50%, we'll say they have cancer, and if it's below 50%, we'll say they don't have cancer, right? That's the way we described it over here. But how could we adjust that if we were more worried about the fact that they have cancer? Instead of 50%, what can I make the cutoff? I don't want to miss people that have cancer, right? So normally the way we do it, like the way we did it over here, was when we only had two classes, right? Whichever one was, if this was above 50%, we would choose this one, right? But let's suppose this was cancer and no cancer. So we're trying to classify them as not computer or washing machine, but cancer or no cancer. Okay? And suppose this was 40 and this was 60, or let's say this was 30 and this was 70. Okay, so what should we do? Well, according to just the straightforward way to do it, we'd say what? They don't have cancer. We'd send them away. But if we're that's probably not so great. All we did was say, there's a 50% chance that you don't have cancer, so you can leave now. It's not such a great, I wouldn't want to go to that hospital, right? So how should we adjust it? Even though this is 30 and this is 70, I might want to change the cutoff for cancer to, if it's 0.05 or above, that it's, if it's 0.05 or above, then I'm going to classify them as cancer. Okay, do you understand? If it's just 0.05, then I'll say there's a chance that you have cancer, so you should go in for further screening. Right, you understand? So even if the chance that they don't have cancer is 0.95, and this is 0.05, I'm still going to send them for further screening. Do you agree? I don't know, which hospital do you want to go to? You want, suppose there's a 5% chance that the test says that you have cancer. You want to just go home and say no? Or you want to get a little more testing? Well, I don't know, I'll leave it up to you. But anyway, we could see how we would want to change this number instead of to 50-50. Instead of 50-50, right? Okay? So we could adjust the cutoff, that's what they're saying. We can adjust the cutoff. Okay? So, and we don't want to make a method where we're stuck with just 50-50. Right? Why not give ourselves flexibility? So why not extend the method a little bit further? Okay? So our approach will be to establish a cutoff value for the probability of an instance being not play and classifying all records above that. So as soon as somebody's probability is greater than 0.05, then I'll assign them to cancer. Okay? Thus, as a first step, we will need to calculate the probability of one class given the value of the predictor. We generally will need to calculate the probability of class CI given the value of the predictor qualities. Hopefully this rings a bell. There are prior slides. Okay. So here's the cutoff probability method. We need to calculate the probability that they're in each of the classes, right? Given the set of predictors, in our case, in this case, we only talked about humidity, just one predictor, but in general, we're going to have more than one predictor. So given a set of values, what's the probability that they belong to each of the classes? What's the probability that they belong to the no cancer class? What's the probability that they belong to the cancer class, given the set of predictors? Okay, does everyone understand? This is what we want to do. Does everyone agree that this is what we're trying to do? We're trying to find the probability of this scenario, right? And we want to do it for each class. So I want to know the probability that they're going to do computer, washing machine, TV, and game. I want to know the probabilities for each one, given the predictor values, given the values of the predictors. What's the probability that they belong to the computer class, the TV class, the washing machine class, the game class? Right? I want to know each of those probabilities. You agree? Once I get them, then probably I'm going to choose the one with the highest probability. Not necessarily, because here, even though this no cancer had a higher probability, I didn't do it. I had the cutoff method. But generally. Anyway, in any case, I want to know what the probabilities are. Whether I'm going to use the cutoff method or any other way, I still want to know the probabilities. So this is now the focus of what we're trying to find. Okay, does this make sense? Okay? Okay, but this can be handled with Bayes' theorem. Right? In case you don't remember. Here. The probability of something given something else, right, can be written like this. Or let me give you another example here. This one. Okay, the probability of A given B can be written as the probability of B given A, and so on like this. Okay. So, here is Bayes' theorem. Now, it looks a little more complicated because I don't have A given B. I have C given a whole mess here, right? Right, I have C given a whole mess here, right? But let me justify the fact that it's really just like probability of C I given just B. It's really Ci given B. That whole mess can still be called B. Why? Because we have, what we have is the probability of C1, for example, given X. Let's say X1, X2, let's just use 3. X1 is what? Humidity, stands for humidity. Humid. X2 stands for windy. X3 stands for, what was another one? Temperature. Okay? So let's suppose, so X1 might be high humidity. X2 might be normal windy, or false, not windy, false. And X3 might be high temperature. Okay, you see what I'm saying? That's what we're talking about, right? We're saying, you know, the probability that it's in a certain class, like they're not going to play, given that the humidity was high, it wasn't windy, and the temperature was high, right? That's the kind of question we're asking, right? But that's actually an event, right? It's actually an event. We could call this event B. What is this event? Remember, events are subsets of the sample space. It's a little hard to visualize that here because we have 3 variables. But anyway, just in normal English, this is an event. Right? The event what? That the humidity was high and it was the windy and the temperature was, humidity was high, it wasn't windy, and the temperature was high. That's an event, right? The event that happened. Right? So given that event, we could call that B. So really, this is just the probability of this given another event. Okay? So that means that we're going to be able to talk about it like this. Right? We're going to be able to talk about switching the order. And so when we switch the order, so to really explain that really carefully, I'd have to spend another 10 minutes. I don't want to go into that, but it's an event. So this whole string here is just an event. So we're allowed to switch it with this one over here by Bayes' theorem. So here we get this to here, and then this. So this is just Bayes' theorem, okay, that we've talked about. Okay? So we have this and this. Now, it looks like, yeah, it's horrible to calculate, but we can get the Weka to do it for us, or the calculator, or Excel, or something to do it for us, so we don't have to worry too much about it. Okay, now, let me skip this for a minute. All right, now, as we said, the problem with having to do this is, what does this say? Read something like this. What does it say? The probability that it's in class 1, let's say the probability that it's not play, given these I'm sorry, no, I said it wrong. I said it wrong. How should we say it? Given that it's not play, the probability that we get these, right? Okay? But still, we still have that problem we talked about, which was this problem here. We're not going to find many people in our database that are exactly like this particular person. So we still have this problem. Okay? Now, so the practical difficulty with the complete Bayes procedure, in that example there was only one predictor, humidity, but what if there were many predictors? This is usually the case in data mining. We want to consider data mining problems with tens or even hundreds or even thousands of predictors. Suppose we have only a modest number, like 20 predictors. In each of those 20 predictors, and suppose they can each take on just 5 values, each one. How many different sets of possible records can we have? So we can have actually 5 to the 20th different records, which is bigger than 10 to the 10th, which is bigger than 10 billion. We can have 10 billion different kinds of records. So how likely is it to have 2 records that are the same? So it's very small. So that we still have that problem. So the solution to the exact Bayes is the so-called naive Bayes. So we're still trying to do this problem. Where did it go? We're still trying to do this, or this, but we have this problem of too many possible cases. So we have a solution now to that. And that is use what's called the naive Bayes. In the naive Bayes solution, we no longer restrict the probability calculation to those records that match the record to be classified. Okay. Before, our basic classification procedure was find all the other records just like it, determine what the classes that they are, that they belong to, and assign that class to the new record. The naive Bayes modification is as follows. For class 1, find the individual probabilities that each predictor value in the record to be classified occurs in class 1. Well, let me show it to you. It's actually that putting it in words makes it really complicated. Okay, so here is what we had, and this is the exact one. Now, we talked about last class about this. Can you remember this? Can anybody make any comments about this statement? Anybody remember what that was? That wasn't always true. That's not always true. Do you remember when it was true?
There is no overlapping area.
No, that was a different one. That was this one. Close, but that was a different one. This was when there were no overlapping areas. That was true. How about this one? This was when we talked about tossing a coin 100 times. Remember, then we said, if you toss a coin 100 times, you get 100 heads. What's the probability that the next one is heads? We said it was 50%. Why? We said the coin doesn't have any memory, right? And another way to express that is, they're independent. So if two events are independent, we showed that this was true. Okay? We did that last time. I don't know how well you remember it, but that's what we did. Okay? So this rule works when A and B are independent. Now, you have to know one thing. In probability notation, when they write something like this, x1, let's say x1 equals, what did we say? It was humid. x1 equals high, humidity. x2 equals, what was x2? Windy. False, not windy. You have to understand that this means, or what would you say, what are we asking for here? We're asking for what? The probability what? That humidity is high, and what's the next word you're going to use? Humidity is, how do you read this comment is what I'm trying to ask you. Humidity is high, and, right? So how do you read the comma? As and. So we have two events that we're saying and. We're saying humidity is high, that's one event, let's call it A, and another event, B, right? So that's A and B. Now how do we write that in set notation? With intersect, right? So we're asking for the probability of A intersect B. Okay? So when we write this, the comma is an and actually. And comma and is the same thing as intersect. Okay? All right? So, and usually they don't bother to write x1 equals high. They just write x1. That's supposed to mean x1 has a particular value. And they just write x2. That's supposed to mean x2 has a particular value. It's not so clear, but that's the way they write it. Okay? So this means that it has a particular value here, and this one has a particular value here. So we're talking about some event A and another event B, and intersect. Now, so if these are independent, then what? How can I rewrite this? Like this, right? So equals the probability of A times the probability of B. Or I guess we could go back here and say equals the probability of x1 times the probability of x2, if they're independent. Okay? So, now, unfortunately, it gets a little bit more complicated because that's called independence. But we have something else that's called conditional independence. So that's A intersect B given C is equal to the probability of A given C times the probability of B given C. So that's called conditional independence. Okay, which is kind of very similar to regular independence. Okay? So, what we want to do, so can you see what we're going to do here? We're going to write x1 given C, x2 given C, x3 given C, and we're going to be able to multiply them. We're going to assume that these have conditional independence. Okay, that's an assumption. Nobody told us that it's true. Nobody told us that these variables are independent from each other. Okay? So it's just we're just saying, oh, let's pretend that it is. And let's make a classifier based on that pretending. But then what can we do? We can see, well, how good does our classifier work for predicting stocks? Well, maybe it works great. Or how well does it do for predicting spam? It might work great, even though we made this assumption that we had independence or conditional independence. I'm not really sure that all these things are actually conditionally independent or not, but it seems to work. Okay, so that's called the naive Bayes classifier when you make that assumption. And it makes the calculations different than before. We don't have to find exact records anymore. okay? We don't have to find them. Nowhere in our calculations will it say, you need to find a record exactly like this. Because this doesn't appear there, where this one is high and this one is false and this one is that. It doesn't say that. After we switch to like this, it just says, you just have one thing that you're looking for, like the proportion of guys that are, the proportion of days that are humid, not the proportion of days that are humid and this, and this, and this. It's just the proportion of days that are humid, the proportion of days that are windy. So that's not so unlikely to have those calculations and to have those examples. So we don't have to find exact matches anymore. So that's the advantage of making that assumption. Okay? So it turns out, like I said, that we get this. So can you see how it happened? Before, I guess I should have pasted that in here. Before, I should have, so you could compare this one with the other one. But before we had this one, here, maybe I should do that now. Copy it, and go to, where is it? Here, no. There it is. Here. Okay, let me put it here. Okay, this is what we had before the assumption of independence. This is just Bayes' theorem. This is just Bayes' theorem, but we take one step further than just Bayes' theorem when we do naive Bayes. We take one more step, we make one assumption. The assumption is conditional independence, which means what? That now here we had and. We don't want that. Because that means we have to find a record that's exactly like the given record. But here, first of all, this is the same. PCI, that's PCI here. Okay, that's the same. But this one becomes the multiplication of x1 CI, x1 C1, x2 C1, and so on. Okay, do you see this, how this works? So that makes the calculations much better. Okay, so we assume that all these different variables are independent of each other. Okay, and so we can convert this one to this. Notice, by the way, in Bayes' theorem, that this term and the first term are the same, and that the numerator term and the first term and the denominator are exactly the same, right? You see that? This is the same as this. But this term is different than this one. So, what's the difference? Here we're doing it for class 1. Here we're doing it for the last class. So it's a little bit, so it's different. Okay, but anyway, we get this calculation. Now, I found this a discussion about conditional independence here. You can check this reference if you want. And you can look at it and you can see where it comes from. Okay, anyway. So does everyone get the basic idea now? All right, so we've done it. We've discussed how naive Bayes works. Okay, what's the key? First we use Bayes' theorem. That allows us to switch the order of A and B. So A given B becomes B given A. And then that gives us this here when we have more than just a single predictor, or when we have more than just a single predictor, we can switch it like this. And then what do we do next, or last? We do the conditional independence, which allows us to split this up into a product. Just like here, we could split this up into a product. Okay, here we have more than two terms, but it's still the same idea. Okay, so now, if we had time, it would have been good to spend like 2 months doing probability and then do this, right? But we didn't have time to do that, so I tried to force it all in just 2 lectures. Okay, but it would be nice if we could really go carefully through all of this probability so that it would be very, very, very clear, but trying to make it clear. All right, any questions so far? That is the naive Bayes calculator, classifier. So now we can try to try it on some data. Okay? But let's take a few minutes break, and then we'll try to do it on some actual data. And maybe look at Weka, see what it does and compare. Okay, so now let's expand the classification to use 2 predictors, humidity and windy. So before we were just using windy, but now we're going to include humidity as well. I'm sorry, windy as well. And let's use the actual Weka data this time. So we're going to try and predict play as a function of humidity and windy. So this is the actual data from Weka. So sunny, hot, high, false, no. And we're just going to use part of it, so we're just going to use these 2 to predict, these 2 to predict play. Okay, calculate each of the 4 possible combinations for humidity and windy. So what are the 4 possible combinations for humidity? Can only take 2 values, and windy can only take 2 values. So what are the 4 possible values together? So you could have it's not windy and high humidity. You could have it's not windy and normal humidity. You could have it is windy and high humidity. And you can have it is windy and normal. So those are the only 4 possibilities, right? So let's figure out what is the probability that it false means not, what does false mean? Not windy and high humidity. So you do that, tell me that. So this is the probability of false and high. Given false and high, what's the probability of yes? How do you do that? So you have to find false and high. So where do we have false and high? How about this one? Yeah, this is false and high. How about this one? No. How about this one? Yes. This one? Yes. This one? No. So it's, we need red in this and blue here, right? So that's 1, 2, 3. Oh, but I'm sorry. Yeah. 1, 2. So those cases, and then this case, and that's all, right? Okay. High, false. Yeah. Right? So it's this one, this one, this one, and this one, right? So how many are there? 4, right? Did I get that right? 4? Everyone agree that I got it right? 4. Okay, now, given that it's, so these are the wrong numbers. I knew there was something wrong here. Okay, so given that it's false and high, what's the probability of yes? These are wrong. So tell me, what should I write here? False and high means what? This one, this one, this one, this one. That's all. So there's 4 of them. And which ones are yes? None of them are yes, right? 2 of them, wait. False, high, oh yes, I have 2 of them. Two of them are, right? So it's 2/4, right? Do you agree? Can I change this number to 2/4? Oops. Where'd that go? So do you agree with me this is 2/4? Okay, good. I don't want it to be Japanese. Okay, how about the next one? Let's do the next one. Okay, given that it's false, false means not windy, and normal. So where are those? False, normal means red and white, right? So 1, 2, 3, 4. You agree? And how many of those are yes? False and normals, how many are yes? 1, okay, 1, 2, 3, 4. I can't do this. What did we say? False and normal, so it's red and white, right? Somebody else do this. 4 of them, and there are 4 cases, and how many of them are yes?
4.
Oh, all of them? Okay, sorry, let's see, you're right. Red, white, yes. Red, white, yes. Red, white, yes. And that's all, right? No, red, white, yes. Okay, so no, all of them. So that was weird. So that's 4 out of 4. Okay, let's do the next one. Or you do the next one. Figure out the next one. So given true high, what's the probability of yes? What do you get?
1/3.
What?
1/3.
1/3. 1/3, okay, good. Let's change that to 1/3. Okay, I don't know what I was doing here. And then, this one, you do it. True normal. True. So it's all white, right? Are they all white are there? 3. Which one do yes? What do you get? 2/3. Okay. Okay, let's see. 2/3. Okay. So maybe that's right. Okay. Now, so I think these numbers are right. Right now, so we just did calculations like this, but the naive Bayes allows us to switch it to this. Right? We just did this. We said, for example, false and high. That's x1 and x2, and then yes. Yes, right? Class 1 is that they play, right? So we just did that, right? Understand? All right, now, but naive Bayes says that instead of doing it the way we just did it, we could try to use this naive Bayes classifier instead. Okay? So this thing, obviously this looks very messy, but actually we only have a few variables, so it's not nearly as messy. So what it says is, for the probability of yes, so we're not doing no, I didn't do any. We could have done no's also, but we didn't do those. We just did yeses. So we're saying, what's the probability of yes given certain kinds of conditions, right? Okay, we didn't do the no calculations. Okay, now, so naive Bayes says that if you want the probability of yes given certain conditions, you can calculate the probability of yes times given yes, what's the probability of the first condition, times given yes, what's the probability of the second condition. And then down here you have to do a bunch of other messy stuff. Okay? Everyone get it? Now, actually, as I already pointed out, this term is exactly the same as this term. And since we have, what's the difference between the terms down here? This part here, this part is the same in each term, except that instead of C1, we have C2 or C3 or Cm. So what does that mean? What are the different Cm's? Those are the different values that the classifier can be, but our classifier is just playing golf or not. So there's only two values that it can be, either yes, they play golf, or no, they don't. So we don't have m different terms here. We have just two terms. One term where C1 is yes, and the other term where Cm is no. So we actually only have two terms here, and they don't have a lot of variables in them. We only have two variables, so it's not nearly as complicated as this general form is. Okay, so what we need to do, the probability of yes, we're going to do this one first. Windy is true, humidity is high. So we already did the exact calculation here. Windy is true, humidity is high. The exact calculation was 1/3. Okay, now let's see, or the actual probability was 1/3. Now let's see what we get when we use the naive. No, I don't think it's going to work too well, actually. But let's see what happens. So what does it say we have to do? We have to do this one. So what is this? It's this, this, and this. There's only three. There's not a million terms here on the top, right? We only have x1 and x2, so we only have two variables we have to do. Everyone agree with that? Okay, so what is the probability of C1 stands for what? What calculation are we doing? Yes. We're trying to figure out the probability of yes. So C1 means yes. So C1 means yes. And so what's the probability of yes? So how many green ones are there here? 9. And how many, so are there altogether? 14. So the probability of yes is what? 9 out of 14. Okay, now this one, how do we do this one? This means what? Given that it's yes, what's the probability of x1? Now what are we trying to do? We're trying to do, in this calculation, yes, x1 is, windy is true. So we're saying, given that it's yes, what's the probability that windy is true? What's that? So given yes, what's the probability of proportion of windy is true? So yet, within the green ones, how many have true windies? 1. I see 3 only. Agree or disagree? So 3 out of 9. Okay? And then the last one is times the proportion of high given yes. So that's the other variable, is humidity variable. So given yes, given the green ones, how many are blue? 3. So that's 3/9. Okay, so we need to do this calculation. That's going to be this top piece here. Okay? Agree? That's going to be the top piece. So I think this is 0.07. Then we have to do so that also goes down here, but we also have to do this one. So what's this one going to mean? Given that it's no, what's the probability of windy? And given that it's no, what's the probability of high? Right, because we did before, so we need to do windy and high again, but this time given that it's no. Okay, so let's make sure I got these right. First of all, the proportion of no, that's this term here, or this piece here. So what's the proportion of no? That's, the other was 9/14, so this has to be 5/14. Okay, now how about this piece? This is what? Given that it's no, what's the proportion of windy? So given that we're in the red, what's the proportion of windy means white. So within the red, which ones are white? I get 3 out of 5. Is that right or wrong? Okay, and then the last one is this one, proportion of high given no. So again, we're in the red, and we want to know which ones are blue. I get 4 out of 5. Do you get 4 out of 5? Okay, so this is 0.17. Okay, now, unfortunately, I don't think it comes out very good, but that's the kinds of calculations that Weka is doing. Okay, so, but we get that. This was for what? This was for windy and high, right? Windy and high. So windy. So this is the, oh, it's not so bad. Not bad. This is the actual number, 1/3, and our naive Bayes estimation of this is not so bad, 0.29. Okay? Oh, I'm so happy. Because it wasn't matching what I did before. It wasn't matching what I did when I was doing it. I was thinking, oh, shoot, I'm going to have to show a bad example of this. Or it doesn't work. Which is possible, right? It doesn't have to work, right? It doesn't have to be, naive Bayes classifier may not be right? But in this case it works pretty well. Okay, so do you see? All right, so now another thing is that we remember we have this idea of cutoff. So what we could do, we just finished what calculation? What was all this? This was this calculation here, right? And what was this for? That was for this, right? And so what was this? This was yes, given, what was it? Windy was true and humidity was high, right? We just finished that calculation, right? Agree or not? We just finished, this was probability of yes, given windy was true and humidity was high. That's what we just did, because in order to do that, we had to calculate this one, and this one. That's what we just did. All right? Okay, so now we found the probability of this. Now, we could use the cutoff value. If we, so if the cutoff value was 50-50, what would you say? If I asked you that, I told you that it was windy and high humidity, would you say yes or no? Well, the probability that it's yes is what? 0.29. So what are you going to say? You're going to say no, right? So we calculated the probability. Then we should also calculate the probability of no, which presumably would be the other, what would be 71%, right? So therefore what? We would predict that they don't play, not that they do play, not that it's yes. Okay, but you could adjust the probabilities, the cutoffs rather, right? We already talked about that. You could have different cutoffs, right? And also, one other thing is sometimes we don't care about the probabilities actually. We just, suppose we had 5 classes instead of just yes, no. we had 5 different classes like Asahi, Kiran, da, 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 then we don't actually care about the actual probabilities, we just want to rank them, which is the most likely, the second most likely, and third most likely. And it turns out when you're interested in doing that the Bayes theorem works even better. The naive Bayes classifier works even better. Okay, so I'll leave it at that for this. And we still have 4 minutes to cover one more topic. So I'll go to this other topic right now very quickly, because part of this is usually included in data mining. So something called lift charts. So suppose that you're a company and you want to do a mail marketing campaign. And suppose it costs $1 for each item that you mail. So we're talking about physical mail. Okay? Or you have any other, you're trying to target your customers and it costs a certain amount of money to target each customer. Okay, so whether it's by mail or whatever way you're going to do it. And you have information on 100,000 customers. Okay? Now, suppose we assume that, we have 100,000 customers. Here's all, we have 100,000 customers, and within that customer, we know that only 10% are going to be interested in our product. We just know that from general past experience. Okay? So we know that only 10% approximately will be actually interested. And it costs us $1 to send out a mailing advertisement to each person, which is kind of a lot of money, right? So if you send it to everybody, you'd have to spend $100,000, right? Which would be pretty expensive. And then if you did it to everybody, how many sales would you make? Only, 10,000 sales, right? Because we said there's only 10% of the people are actually interested. So a lot of those are going to go to waste, right? All those marketing dollars are going to be wasted, right? So, now suppose that we had a model, so that's in the absence of any modeling, okay? But suppose we had a model which will forecast or classify people as being interested or not interested, okay? And maybe the accuracy of that model is 80% or something. So if it says they're interested, maybe we'll use a naive Bayes classifier, and it turns out that the accuracy is about 80%. So the probability that if that they are actually they will buy, given that the model says buy, is say about 80%. Okay? Given that the model says to buy, that they will buy, that they actually buy, let's call it actually buy, is 80%. Okay? That's a pretty good model. So the question is, how can we use this to reduce our costs? Is there any way we can use this to reduce our costs? So we have this classifier. So let's say we have some data about all these 100,000 people, and like we know their age, and we know their income, and we know their gender, and so on, right? And then based on that, we have a model which will predict whether they're going to buy or not. Okay? And we know that about all these people, all the 100,000. What could we do to reduce our costs? We could use the model on each person in our set. Presumably that wouldn't cost very much to do that, maybe just a few buttons, click a few buttons on the computer, because we already built the model, and we can predict what the probability is that each person will buy. Let's suppose this was the naive Bayes model, so that it gives probabilities for each, whether they will buy or not, right? It doesn't just say whether they will buy or not, but it gives the probability that they will buy. Okay? So we have for each person, so let's imagine we had the list of people, person, so person 1, person 2, person 3, person 4, right? And then we have the probability of buy, right? And we could arrange this list in order of who's most likely to buy. So this person is 90, according to naive Bayes, there's a 99% chance that they will buy. And this person is 98%. This is also 98%. And this is 97%, and so on, right? Okay? We could do that. We could, a few clicks of the buttons, and we had the data on all 100,000 people, we could do this. Now how could we kind of reduce our costs? Well, if we market to everybody, we're not gonna reduce our costs because we're just gonna have to pay 100,000. But we could choose just to market to the people that are very likely to buy, right? Like maybe we'll just market to the 10,000 people that are most likely to buy. And then, we'll pay, how much will it cost us? $10,000, and virtually every one of those people will actually buy because there's a very high chance that they will buy. But if we don't have the model, we don't know which 10,000 to limit it to. Right? We don't have any information, we just have to randomly select people, right? But if we have the model, we can do this, right? So if we don't have the model, let this be the number of people that we market to. So the total number of people is 100,000. And how many people, if we market to all 100,000 people, this is the number that buy. Number that buy. How many will buy if we market to all 10,000 people? 10,000, right? I'm sorry, if we market to all 100,000 people, how many will buy? 10,000, right? So this is 10,000, right? That's what we said, because at most 10% will buy. Everyone agree? Everyone know what I'm talking about? So if we market to only 50,000 people, approximately how many will buy? Approximately 10% of that, which is 5,000 people, right? So this is 5,000. 5,000. So this dot is there. And if we did here, it's going to be here. It's going to be this line, right? If we market to 50,000, we expect about this many will buy. If we market 100,000, this many. And this line determines basically how many people will buy, right? Depending on how many we market to. However, if we use our model, we expect to do better than this, right? Maybe if we market just to, if we market just to 10,000 people, here, we might get 9,000 that will buy, right? So we might get this dot here, do you agree? And if we market to, 5,000 people, we might get like this dot here, okay? So we might get a curve that looks like this. So what do I mean by this? This is if we use our naive Bayes predictor or some other predictor. Then we can get virtually all the same people that we would have gotten if we just used it at random. All the 10,000 people, we can get virtually all of them just by sending out 10,000. So this curve represents what we could get with our model, if we use our model, right? So this is called a lift chart. So we can do better based on, now if we, if we market to all, even if we use our model, but we end up marketing to all 100,000, we're going to still get the same 10,000 people to buy, right? So it doesn't help if we do that. But if we stay over in this area, we can get much better lift based on using the model. And so this is called a lift chart, okay? And I forget how they measure how good it is, but basically it might be like some distance from here to here, or something like that. There is some measure of how good the lift chart is. Or also, they also use this. the distance of this to here. This is the optimal point, right? That means, I mean, that actually isn't even possible, right? Because you can't send out no, well, no, it is possible, sorry. You could get everybody to buy even if you only send out, if you didn't send out anything. I don't know how that would happen, but anyway, this is kind of the optimal point, so they might measure this distance, or something like that. Anyway, there are different ways to measure how good it is, but you can see that there's an improvement. They also might measure this area to say how good a lift is. Okay, so that's called a lift chart. You can read about lift charts on the internet, but that's the idea. Okay? There's one other chart we have to talk about, we'll talk about it next time, called an ROC, an receiver operating curve. And that's used to compare different models. Okay, this can also be used to compare different models. So if we use one model, we might get this curve, and if we use another model, we might get this curve, right? So we can say which one is better. And then we'd like to have some way to compare some numerical measure of each one. And that's what I was talking about. Okay, so that's the lift curves, and we've done naive Bayes, basically. You've seen how it works. We've seen the mathematics of it, and it should work exactly like that. Now, last thing, one student asked me, is this. This here. Do you see here? This is from WECA. Of course, you would like to know, and we never went through it, but I can show you in a minute, but you would like to know, these are the different instances for the weather data, the golf playing data. So there were 14 instances, right? There were 14 records. You'd like to know which one did WECA get right and which one did it get wrong, right? We never looked at, we said, oh, it got 80% right. We don't know which ones were right and which ones were wrong. Okay, so let me show you that too, if you have a second. So in WECA, if you want to do that, you do this option. So let's say we open up the same data set. Called weather nominal, same one we had before. And let's use the naive Bayes. So you get Bayes classifiers here, and naive Bayes or naive Bayes simple. I'm not quite sure what the difference is. So let's use that. Now, if you just do, let's say, do it on the training set. If you just do this, you get the results. So how well did it do? 97%, 92%. Okay, it's very good. All right, now, but you don't know, and you also have this, right? So you know that, what does this mean again? What's this one mean? It means that there was one case where what? It was classified as A, but it was actually B. Now A stands for yes, so it was classified as yes. So we said they were going to play, but they actually didn't play. So there was one case, but we don't know which of the cases it was. If you go to here, let me save this as a CSV file on the desktop so we can look at it. Okay, you don't know which one of the cases was the one that was wrong. Here's the cases. So there was one case where we said that it was what?
Yes.
We said that it was yes, but it was actually no. So it was actually no. So it's one of these no cases. This one, or this one, or this one, But it's one of these, but we don't know which one, right? Do you know which one it is? One of these, we said it was yes, but it was actually no. So it was one of these cases, but we don't know which one, right? Okay, but you can know by doing this. You go to here, you go to more options, and it says output predictions. Currently, we're not outputting the predictions. You can choose the format, so the simplest one is just plain text. Just plain text, and click OK, and then do it. And now, here. So which one is it? It's number 6. So it was actually no, but we said yes. So let's see if we got it. Let's see if that's possible. Number 6. Yeah, it's this one here. So this is the one that it made a mistake on. Okay? So naive Bayes said that this was going to be yes. So it was when it was rainy, cool, normal. Okay? And windy. Okay? You understand? So you can see that if you choose that option there. Okay? And it kind of tells you some stuff. I'm kind of confused about their output here. Like this, I thought this is the probabilities. I don't think it is. Because if it was the probability of like yes, and I don't know what this is actually, these numbers. Okay? If anybody can figure that out, let me know, please. I don't know what they set up here in Weka. The manual is not really great. Okay? Okay, that's all.